Okay, great. Yeah, so hi everyone. I'm really glad to be presenting this paper at this workshop. I think it fits the theme really well. And even though it's sort of old work for me, but I guess recently I haven't done as many algebraic type papers. So this paper is about symmetries, graph properties, and quantum speedups. My name is Daochen, and this is joint work with 5 great co-authors. So Chailloux and David, Andrew Childs, Andrasky, and William Kreshmer and Sebastian Potter. And you can find the full version of everything I'm going to be talking about at this archive link. Okay, so we'll be talking about quantum speedups and symmetric functions. So what are they? To talk about speedups, we need the notion of classical and quantum query complexity. So suppose we have an F going from a domain B, which is some subset of sigma n, where sigma is some finite alphabet, to naught 1 is a known function. We ask how many positions of input x and d are necessary and sufficient to query to compute f of x with high probability in the worst case. The answer is denoted R of f and Q of f in the classical and quantum cases, respectively. Quantumly, we can query x in superposition. That is, we can feed into the algorithm a superposition over the indices I with amplitudes alpha I, and we can get out kind of that same superposition, but now with the value of the input x loaded into a second register. So that's the xi here. So it is a fact that R of f is at most Q of f, and this is because we can always simulate a classical and possibly randomized algorithm quantumly. And in fact, the allowance for randomized algorithms is the reason why the classical query complexity is denoted with a R. So to get a flavor of this complexity measure, let us think about the classical query complexities of the following 3 functions. So the first function is a simple finite example with n is equal to 3. It maps 3 bits encoded in x to x1 and x3, or x2 and not x3. Now, of course, you can compute this function f by querying all 3 positions of the input x, namely x1, x2, and x3. In fact, doing this, that is querying all positions, suffice to compute any function. However, if we look a bit closer at this, this example, you can see that f can in fact be computed using only 2 classical queries. What you would do is you first query x3. If x3 turned out to be 1, then you know sort of the second part of this formula won't come into play because not x3 will be 0. So the second part of this formula gets zeroed out. Then you only need to look at x1 to determine what f is. So that only takes 2 queries. And likewise, if x3 is equal to 0, you don't need to look at the first part, and you only need to query x2. So this example shows that sometimes there can be some non-trivial kind of quantities coming into the query complexity. And I should also mention that this f, in fact, in some sense, does depend on all 3 positions of x, but its query complexity is still 2. Now, a second example would be the OR function. Now, this function is defined to be such that it's 1 if and only if at least 1 bit of x is 1. So it's only 0 on the all zeros input. And finally, we can think about the parity function. The parity function maps input x to 0 if x contains an even number of 1s, and maps it to 1 if it contains an odd number of 1s. So what are the classical query complexities for OR and parity? If we sort of sit down and think about this for a bit, we'll see that they are both kind of about order n. And let's take OR. The reason for having order n is because you might query the first n-1 bits of the input, and they might all turn up 0. And at this point, you kind of still have to query the last bit, because the last bit might be 1, which might determine what the value of OR is. So that is an argument that in fact shows that omega n lower bound for deterministic algorithms and a lower bound of n for randomized algorithms can also be proven with a little bit more technical work. So from what I just said, we can see R of OR is theta of n and R of parity is theta of n. So I know that this audience might not all be computer scientists. So in this talk, I will be indeed using a lot of this like big O notation, theta notation, and omega notation. So if you see this, basically don't worry, you just think of kind of O as being less than or equal to, theta as being sort of equal to, and omega as being sort of at least for this talk. Okay, so what are quantum speedups in query complexity? So given a family of functions f, we ask when is R of f super polynomially larger than Q of f, in which case throughout this talk I'll be referring to as a large quantum speedup. And also when is R of f only polynomially larger than Q of f, in which case I'll be calling that a small quantum speedup. Here are 3 examples of quantum speedups. 2 are in the small camp. So the first is the OR function, which we have just seen, with D set to be the set of OR bit strings. We have just seen that of this function is theta n. And in fact, by Grover search, we can show that the quantum query complexity of this function is theta the square root of n. So in Grover search, you want to find a marked item, and to compute OR, that's exactly what you're trying to do. You're trying to find if there's the 1 in the string that is given to you. So in this case, we see that there's a kind of a quadratic difference between R and Q is kind of quadratically faster than R. A second example in the small camp is F equal to ED, short for element distinctness. In this example, the domain D is sigma to the n, where sigma is bracket n, and throughout this talk, you'll see bracket n coming up a lot, and that's simply the set 1 up to n. So this function, what it does is it basically takes kind of a length n string where the string entries are in bracket n, and it outputs 1 if there are kind of 2 distinct positions that have to contain the same entry. So if you have like a string like 1, 1, 2, 3, 5, 6, that will output a 1 because there are 2 1s. If you have a string that's kind of like 1, 2, 3, 4, 5, 6, that will output 0 because there are no sort of non-distinct elements. So for this function, it is known that R of f is again theta of n, but Q of f is theta of n to the 2/3. So that is again a polynomial speedup, not as much as in the OR case, but still kind of a meaningful amount. But I suppose the reason why many of us are interested in kind of quantum computing and why there's so much investment in this area is because we're kind of interested in large quantum speedups. And an example in this category is when f is the so-called Simon's function defined by Simon in 1997. This function, before I describe it, I'll just tell you that it has R of f equal to theta square root of n and Q of f equal to log of n. So you see sort of R of f is sort of super polynomially, in fact, exponentially larger than Q of f. The function is sort of defined in a kind of a special way, and it has sigma equal to bracket n, where n is some power of 2. We'll view the n positions of input x and d as being labeled by bit strings of length k. The problem is such that you're promised the input satisfies one of 2 things. Either the xi's are distinct for all I in bracket n, in which case the function outputs 0, or there exists an a not equal to the all 0s bit string, such that xi is equal to xi XOR to say for all I in bracket n, in which case the function evaluates to 1. So if you look at this, you might be reminded of some sort of periodicity condition, and that's kind of precisely what it is. And in fact, Peter Shaw noticed this and was inspired by the large quantum speedup exhibited in query complexity for this function to come up with his famous Shaw's factoring algorithm that relies basically on some sort of period finding, but in a different group. Instead of here, it's sort of the, I suppose, the Z2 to the N group. Shaw's algorithm works over Z. So these examples show that query complexity capture kind of a lot about what we know about quantum speedups, and it motivates us using query complexity as a measure of quantum speedups. Okay, so the focus of our work is to characterize how the symmetry of a function relates to the quantum speedup it admits in query complexity. Now, group theory is the mathematical study of symmetries, and we say a function f is symmetric under a permutation group G on bracket n if for all permutations pi in G, the domain is invariant on the pi, so that's the first condition. And secondly, the function itself is invariant under pi. I'll just briefly note that the second condition only makes sense given the first condition, because otherwise the permuted version of x written as x composed with pi might lie outside the domain of f. So for those unfamiliar with group theory, you can just think of G as a set of permutations of bracket n that is closed under composition, meaning that when you compose those permutations, you never end up outside of G. So here are some examples of symmetric functions. We have our friend from before, the OR function. We can actually play around with it a little bit. We can restrict the domain to be such that it only contains all the bit strings with Hamming weight at most 1, meaning that the is at most 1, 1. So this domain, if we look at the first condition, it is satisfied because however we permute the domain, we still end up in the domain. And moreover, the second condition is satisfied because whether a string has a 1 or not, which is the defining condition for the OR function, does not change, however you permute an input string. It can also be easily seen that the element distinctness function also satisfies this property of being symmetric under all the permutations possible of bracket n. So to say that they're symmetric under all the permutations is equivalent to saying that they're symmetric under the so-called symmetric group denoted Sn. So Sn by definition means the set of all permutations. So Aaronson and Ambainis in 2009 and Chailloux in 2018 showed that for any function that is fully symmetric, we can only expect to get at most small quantum speedups. Now, our main example in this work is to consider when f is a graph property in the adjacency matrix model. In this case, the group of symmetries under consideration are graph symmetries. We will show that graph properties in the adjacency matrix model do not admit super-polynomial quantum speedups. So to make sure we're all on the same page, let me just say what the adjacency matrix model of graphs is. So in the adjacency matrix model, a simple graph on n vertices is modeled by a symmetric n by n matrix. So here's an example with n is equal to 4. The graph on the left is modeled by the matrix on the right. Basically, the ijth entry in the matrix indicates the presence or absence of the edge ij. So let's just do one example. So this entry, I guess, row 3, column 2 has got a 1 in it because the edge 2, 3 is present. Now, there kind of a matrix is somewhat difficult to fit into the bit string or like string framework we were discussing just a bit earlier, but actually that's no big deal at all because we can simply kind of collapse this matrix into an n choose 2-bit string by, just concatenating kind of all the entries in the matrix. Note that we don't have to kind of, also put in the other side because it's a symmetric matrix and doesn't give any extra information. So this graph as a bit string would be modeled by 1, 0, 0, 1, 1, 0. That is, I just concatenate the first row in red, the second row in red, and the third row in red. So to be completely clear, the second bit indicates, for example, whether edge 1, 3 is present. And in this case, 1, 3 is not present. That's why it's a 0. Now, a graph property in the adjacency matrix model is a function f from a set of graphs specified in the adjacency matrix model to not 1 that is symmetric under graph symmetries, i.e. graph isomorphisms. So for example, a graph property might be whether or not a graph has a triangle. So this is the triangle property, and it does not change for kind of isomorphic graphs. That's why it is a graph property. Two isomorphic graphs either both have a triangle or neither has a triangle. So as a second example, any graph property f must evaluate to the same value on the following two isomorphic graphs. So the left one is clearly isomorphic to the right one, but I'll stress that the graphs in terms of the adjacency matrix are not the same. The left one is exactly what we have seen on the previous slide, and its bit string representation is 1, 0, 0, 1, 1, 0. But the right one is different. It's 1, 1, 1, 0, 0, 0. Maybe just to see the difference in the second bit. So the second bit indicates whether edge 1, 3 is present or not. So in the first graph, 1, 3 is not present. That's why it's 0 for the left one, and but edge 1, 3 is present for the right graph. That's why it's a 1 in the right one. Okay. So the set of graph symmetries of a graph with n vertices is denoted Sn2. Sn2 is a permutation group on bracket n choose 2 of size n factorial that is naturally induced by Sn. And it's defined in the following way. So we identify bracket n choose 2 with the set of possible edges on n vertices. So that set has size n choose 2. Then Sn2 consists of permutations that map edge ij to sigma I, sigma j, where sigma is an element of Sn. So for example, when n is equal to 4 and sigma is this permutation in S4, maybe let me just pause for 1 second here to say what this notation means. This is sort of some standard group theory notation, but it just means that this sigma maps 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So this sigma in Sn would correspond in Sn2 to the permutation that's shown on this slide, and basically according to this correspondence. So let's maybe just take one example, like the edge 1, 3 got mapped to edge 2, 4 because sigma maps 1 to 2 and 3 to 4. I'll remark that Sn2 is much smaller than the set of all permutations on bracket n choose 2. For example, when n is equal to 6, the size of Sn2 is just 6 factorial, which is just 720, whereas 6 choose 2 factorial, which is the size of the set of all permutations on bracket n choose 2, is about 1.3 trillion. Therefore, it is much less restrictive for a function to be symmetric under Sn2 than all permutations. In fact, for each integer p, there is the set of p uniform hypergraph symmetries of a hypergraph with n vertices. This is denoted SNP and is defined analogously to SN2. I'll just note that a p-uniform hypergraph is a natural generalization of a graph where each edge, instead of kind of generalized edge, instead of containing only 2 vertices, now contains p vertices. Okay, so we are going to show that there does not exist a super polynomial quantum speedup for graph and hypergraph properties in adjacency matrix model. And our proof really builds on a previous proof by Chailloux in 2018, which showed kind of the result in essence for p is equal to 1. That is when the symmetry group is the full set of permutations, namely Sn. So suppose we have F symmetric under Sn. His argument goes as follows. So given an algorithm for computing F, if we replace the input x in D by x permuted by pi for a random pi in Sn, and by random I mean uniformly random, then the algorithm still correctly computes F. That's because F is symmetric under Sn. Now, the main idea is that we will replace a random pi in Sn by a random range R function alpha from bracket n to bracket n with the size of the image equal to R. If a quantum algorithm distinguishes x composed as pi, so that's just x permuted by pi, from x permuted by alpha, then it distinguishes pi from alpha. In other words, if it cannot distinguish pi from alpha, then it cannot distinguish pi composed with, x composed with pi from x composed with alpha. Now, there's a theorem due to Mark Jandry from 2015, which says that distinguishing a random range R function from a random permutation in Sn needs at least R to the 1/3 quantum queries. So if we, in this theorem, take R to be Q of F cubed, then it implies that a Q of F cubed to the 1/3 power, which is equal to QF, query quantum algorithm, cannot distinguish x composed with pi from x composed with alpha. And now for the punchline, which is that a quantum algorithm that computes using x composed with alpha can be simulated with only R classical queries. Why is this? Well, x composed with pi kind of, by definition, only has essentially R kind of non-trivial indices, because if you feed in an index to x composed with pi, composed with alpha, sorry, alpha only has range R. So there are only kind of R positions in x composed with alpha that will ever be used by the quantum algorithm. So a randomized algorithm can simulate this simply by querying those R positions that the quantum algorithm ever uses. I'll note that this argument doesn't talk about anything to do with time complexities, and so what the randomized algorithm can do in terms of non-query operations, it can just brute force simulate whatever the quantum algorithm is doing. But the key point is that the number of queries the randomized algorithm performs is only at most a polynomial function of the number of queries the quantum algorithm performs. And this implies that R of F is at most order Q of F cubed. So that is Chailloux's proof. In our paper, we sort of generalize this approach to graph symmetries. So let G be a permutation group on bracket n. Suppose now we need at least R to the 1/C quantum queries to distinguish a random range R function from a random pi in G. We'll say such a G is well shuffling with exponent C. Then by exactly the same argument I just described of Chailloux's, it implies that R of F is at most Q of F to the C for all F symmetric under G. Now for graph symmetries, let us first consider G as Sn bracket 2. Note that this is not the same as Sn2, which we had been talking about just a bit earlier. So Sn bracket 2 on bracket n squared is the set of permutations that map ij in bracket n squared to, now this no, it's a tuple and not a set, maps this tuple to the tuple of pi I, comma pi j for pi in Sn. Our argument goes as follows. If we can distinguish a random pi in Sn.
Hello, can I ask a question? So
yeah.
So this gives me an opportunity to ask a question I wanted to ask earlier.
Yeah.
So how is, I mean, you earlier compared Sn upper index 2 to S2n, and you remarked that S2n is a much larger group. But how is Sn upper left?
Yeah, it's a bit difficult to hear.
Okay, maybe let me move closer to the mic.
Yeah.
You said earlier that S2n, the permutation group on 2 elements, is much larger than Sn. Okay, so far so good. But you have this object Sn upper index 2 introduced, in which is it different from Sn as a group? That's my question.
So is this a group? Is that your question?
Yes, I would think it is. And if it is, how does it relate to Sn?
Yeah, so Sn2 is it's sort of a permutation group acting on bracket n choose 2.
Yes.
So, and I'm saying that on bracket n choose 2, you can consider two things acting on it. One is Sn2. Another thing is S subscript n choose 2. And I'm saying S subscript n choose 2 is much bigger.
Yeah, but I mean, this action on the edges is determined by the action on the vertices.
Yes.
And so how does this object relate to Sn?
Oh, yeah, I mean, it relates to Sn precisely by this correspondence, right?
So it seems to me that it is the same as a group, or is it not?
Oh, I mean, yeah, yeah, they should be isomorphic as groups, I think. Yeah, that's right. I mean, I think that, yeah, so they definitely have the same size. Yeah, and I think they're isomorphic as groups, right?
Okay. Make sure that I'm not missing anything.
Okay. Yeah, thanks for the question. Okay, so I think we were here, somewhere here. Yeah, so and actually it's good that we just refreshed our memory of what Sn2 is. So it's a bit different with this Sn bracket 2. It's, you know, superficially it looks pretty similar, and that's why kind of in this slide I'll just argue something about Sn bracket 2 and say the same holds for Sn2. So the key argument is sort of this paragraph, which is that, yeah, if we can distinguish a random pi in Sn bracket 2 from a random range R squared function on bracket n squared using Q queries, then we can distinguish a random tau in Sn from a random range R function on bracket n using 2Q quantum queries. So this is because we can instantiate a single query to a random pi in Sn2 bracket 2 using two queries to a random tau in Sn, or alternatively instantiate a single query to a random range R squared function on bracket n squared using a single query to a random range R function on bracket n. But by Jandry's theorem mentioned earlier, we know that kind of doing this latter task of distinguishing a random tau in Sn from a random range R function on bracket n takes at least R to the 1/3 queries, which, you know, is equal to R squared to the 1/6. We see that Sn is while shuffling with exponent C is equal to 6 by the definition at the top of the slide. So we started with trying to distinguish a random pi in Sn bracket 2 from a random range R squared function. And if we look at the definition of while shuffling, kind of we see that this R squared is the same as this R squared, and the exponent is 1/6, and therefore, by the definition of while shuffling, the C is 6. So that's Sn bracket 2, and as I hinted at, we can similarly argue that this same holds for Sn2 on bracket n choose 2. Also, in fact, with the same exponent, and the argument even generalizes to show Snp on bracket n choose p is while shuffling with exponent c is equal to 3p. Okay, so that's our result for graph symmetries and graph properties in the adjacency matrix model. What about other symmetries? So for this, we now are going to examine the situation when the group is a primitive permutation group. So a permutation group G on bracket n is transitive if basically it can map kind of any two elements x, y in bracket n to each other. And the permutation group G on bracket n is primitive if it is transitive, and the only partitions of bracket n preserved by G are sort of the two trivial ones, the partition into just G itself and the partition into sort of singletons. So here's an example of a G that is transitive but imprimitive, so that we can see the definition is sort of non-trivial. So let n is equal to 4, we can consider the permutation group generated by these two permutations. So the first permutation maps swaps 1 and 2 and 3 and 4. The second permutation swaps 1, 3 and 2 and 4. Now G is transitive. We can definitely get from 1 to 2. We can also get from 1 to 3 by going from 1 to 2 using the first permutation, going from 2 to 4 using the second permutation, and then going from 4 back to 3 using the first permutation. And you can see that it is transitive for all of the other pairs you might think of. But it preserves this partition B into B1 and B2. So B1 is the set 1, 3, and B2 is the set 2, 4. So 1, 3. So let's just map the first element onto this partition. So 1 gets mapped to 2, 3 gets mapped to 4. So B1 just becomes B2, and B2 will become B1. So this partition remains invariant under this permutation group. So it is imprimitive. To characterize how quantum speedups behave with respect to primitive permutation groups, we need to first talk about the base, a notion of base of permutation groups. So a base of a permutation group G on bracket n is a subset of bracket n such that if H is in G and H of x is equal to x for all x in S, then H is the identity element in G. And the base size B of G is the minimal size of a base. So here are some examples. The first one is S3 on bracket 3. This has base size 2. It is not size 3 because if you know how an element behaves on 1 and you also know how it behaves on 2, you already know how it behaves on the third one. And so it is kind of 2 and not 3. And similarly, Sn on bracket n has base size n-1, and the base is 1, 2, up to n-1. A more interesting example is when the group G is this GRN of F2, which is the set of invertible n by n matrices over F2. This group acts on F2 to the n, and it has base size n. A base is the set of standard basis vectors of F2n. I'll note that the base size here is very small in the sense that it equals to the log of the set that it acts on. So this set for the base only has size n, but the size of the thing G acts on has size 2 to the n. And then this notion of small base will come up in the next slide. And the last and important thing to note about base size is if H and K in G agree on a base, then H must be equal to K. This is because H times K inverse would then fix the base. And by definition, if it fixed the base in the sense that it maps every X in the base to itself, H times K inverse must be identity, which means H must be equal to K. So the upshot is, if you know how H behaves on a base, you can identify H. So what do bases have to do with quantum speedups? And here's a theorem in our paper. So let G be a permutation group on bracket N, and let F be a function. We show that there exists an H that is symmetric under G, such that the quantum Carré complexity of H is at most the quantum Carré complexity of F plus the base size of G. And on the other hand, the randomized Carré complexity, or the classical Carré complexity of H is at least the classical Carré complexity of F. Before I go to prove this theorem for you, let me just say what the meaning of this is and the corollary is. So the corollary is, if G has base size equal to n to the little of 1, which just means some function that grows slower than any polynomial in n, then there exists a function symmetric under G that emits a super-polynomial quantum speedup. So the motto is, small base size implies there can be a large or super-polynomial quantum speedup. The proof of the corollary is really simple. So in the theorem, we just take f to be Simon's function. Then we have seen that q of f is equal to order of log n, but r of f is omega square root of n. Therefore, this h, which is symmetric under G, has q of h is at most q of f plus b of G, which is order log n plus n to the little of 1, which is equal to n to the little of 1. For computing H. But now the important point is that H is symmetric under G. Okay, so how do we prove this? So here's a really kind of sketch, and with n is equal to 2 as an example. So we take n is equal to 2, we consider D to be the set of 2 elements, each being a tuple, the first one being A comma A, the second being B comma A. And we consider G to be just S2, so this just contains the identity element and the transposition one that swaps 1 and 2. We will construct the set D tilde of so-called G permutations of D as follows. So what we do is we take the first element in D, we permute it according to the 2 elements in G. So the first element in G permutes A comma A into sort of this thing in D tilde. The second transposition in G, or the swap operation in G, permutes A comma A into this second element of D tilde, and we likewise do the same for B comma A. So that's why there are 4 elements in D tilde. We'll now let H, which is a function on D tilde, to be basically the same as F, in the sense that H will map the first 2 elements to whatever F maps A comma A to, and H will map the second 2 elements in D tilde to whatever F maps B comma A to. Then kind of by the definition of H, it is symmetric under G. But Q of H is at most Q of F plus B of G by the following algorithm. So recall Q of H is the quantum Carré complexity of H. So to show an upper bound of this form, we just need to come up with a quantum query algorithm that computes H. And that algorithm is as follows. We'll classically query the indices in the base of G to identify the G permutation. Then we will sort of reverse this permutation so that sort of this an input like that looks originally like A comma 2 comma A comma 1 becomes in some sense unscrambled and becomes kind of in the clear kind of in a form that F can take as an input. And then we would simply use F to compute whatever the value of we'll use the algorithm for computing F to compute whatever the value of F of the input is. Okay, so that is the the bound for Q, upper bound for Q, the lower bound R of H is at least R of F. Sort of intuitively already sort of makes sense, because if you look at the definition of H, it already looks more complicated to compute than F. But I guess more formally, we can easily see that an algorithm for computing H can be used to compute F with no extra overhead. So yeah, so back to primitive permutation groups. The reason why we have spent 2 or 3 slides talking about bases is because of this amazing theorem of Liebeck from 1984, which says that if you have a G that's a primitive permutation group on bracket n, then exactly one of the following 2 cases hold. In the first case, n is equal to n choose p to the l's power, and G contains permutations of bracket n, which is equal to bracket n, m choose p to the l, that permutes each of the L entries according to AMP, which is a subgroup of SMP. So AMP, you can, for the purposes of this talk, you can pretty much think of as essentially the same thing as the P-uniform hypergraph symmetries. For experts, they are the subgroup of SMP that contain the even permutations. So that's the first case. The second case is the case where the base size of G is essentially small. It's of like order log n. And the consequence of this theorem, together with what we just discussed about how base size relates to quantum speedups, and also a bit earlier of how graph symmetries relate to quantum speedups, is the following. We get a complete characterization of quantum speedups for functions symmetric under primitive permutation groups. So in case 1, this is essentially hypergraph symmetries, and we know that we have shown that there can only be polynomial quantum speedups. Maybe a quick caveat, we showed it for L is equal to 1, but showing it for larger L is straightforward, because essentially this is the group involved here is sort of just a direct product of the groups we have previously considered, and direct products are sort of easy to handle. In the second case, we said that a small base size implies a super polynomial quantum speedup, and that's kind of covers the second case. And we have our complete characterization theorem for primitive permutation groups. So lastly, the reason why we care about primitive permutation groups is because they allow us to go and generalize even further to general permutation groups. I would just stress and recall that the prior art kind of in this whole direction was this paper, these 2 papers by Aaronson and Ambainis and Chailloux, who showed that there can only be small quantum speedups for F symmetric under the full symmetric group. In our work, after noting also that general permutation groups are in some sense built from primitive permutation groups, and for experts, they're built by this notion of kind of Rees product, we can show this following almost near complete characterization theorem of how quantum speedups functions symmetric under any permutation group, characterize the quantum speedups for functions symmetric under any permutation group. So maybe let me just give a quick rundown of this chart here. So you start with a permutation group. If it has small base size, then you know that there can be a large quantum speedup. If it has large base size, but it's primitive, then by the theorem of Liebeck, we know that it has adjacency matrix hypergraph symmetry, so necessarily small quantum speedup. If it's imprimitive, but breaks into sort of a non-constant number of primitive groups, then there's also a possible large quantum speedup. If it breaks into a constant number of primitive groups, at least one of which has small base size, then it's large again. And finally, and this is sort of a question that's open in our paper, we haven't resolved this, is when it breaks into a constant number of primitive groups, but none has small base size. In this case, we are not sure. So that's sort of our main result in terms of a characterization theorem for symmetries and quantum speedups. You'll note that I have been stressing the words adjacency matrix a lot during this talk, and you might be wondering, is that just because I'm very pedantic? But in fact, that's not the case. And in the same paper, we also show that there can be exponential quantum speedups for computing graph properties in the adjacency list model. So I'll be a bit more succinct here because I think this has less to do with the topics and themes of this workshop, but I do want to give you guys just a flavor of what's happened in this part of our paper. So in the adjacency list model of graphs, a graph on n vertices of degree bounded by d is modeled by a list of length n times d. So here's an example with n is equal to 4 and d is equal to 3. So, okay, so this graph is our friend from before. And the first row is 2 perp because it kind of contains a list of neighbors of the first vertex. So the first vertex has the neighbor 2, but it has no other neighbors. That's why it's kind of only 2, and then it's like sort of blanks in the second and third positions. The second vertex has all 3 neighbors present, and has 3 neighbors, and so that's why in the second row it has 1, 3, 4, and so on. So this is the adjacency list model. Now, we show that there's a super polynomial quantum speedup for graph property testing in the adjacency list model, where property testing means that you're given a graph that is promised either to have a property or is far from having it, and you want to decide which is the case. So graph property testing is a central area of study in theoretical computer science due to its rich history, surprising results, and kind of widespread applications. And the main idea of getting our speedup is to upgrade this blue trees problem, which has the super polynomial quantum speedup in the adjacency list model, to a graph property testing problem. I'll just briefly say that why this original problem, this original famous blue trees problem, is not a graph property testing problem. It is for 3 reasons. Number 1, so is that maybe before I say that, let me just say what the glue trees problem is. The glue trees problem is you're given sort of the vertex number of the vertex labeled entrance, and the task is to find the vertex number of the vertex labeled exit. And it is known that there is a quantum algorithm that solves this problem in polynomial in n number of queries, where n is the depth of this graph, whereas it is also known that any classical algorithm needs about 2 to the n queries. So this is not a graph property testing problem for 3 reasons. Number 1, the vertex number of entrance is given, which is disallowed in property testing. Number 2 is that the answer to the problem for isomorphic graphs can be different, which actually shows it's not even a graph property. And third is that there is no notion of being given a graph that is far from the given graph. So it's not in the form of a testing problem. So to do the upgrade, what we construct is sort of the graph property that asks us to decide whether a graph is of the form shown on this slide. So let me just explain quickly what the graph is. So each candy-shaped graph consists of a body and 2 antennas, where the body is a blue trees graph and the antennas are binary trees. So the double edges go between vertices in the body and antenna. See, there's a question. Yeah, I'm about to wrap up. What was I doing? Yeah, so the double edges go between body and antenna, and these circles represent sort of self loops at kind of the intersection between the body and the antenna. So the idea is that we can classically test the entire glued trees graph if the leaves of the 2 glued trees, so the leaves are these vertices in the middle, are somehow kind of marked or distinguished in some way. This is because the problem then reduces to testing balanced binary trees, which we know how to do even classically. Now the trick is to mark the leaves in a way that a quantum algorithm can read efficiently, but a classical algorithm cannot read efficiently. So to do this, we basically connect vertices in the leaves by a double edge to a candy graph that has an even parity of circles on both ends. And a quantum algorithm can determine this parity easily by running the algorithm used for the glue trees problem. So it can, start from this vertex, follow this double edge to the corresponding candy graph. Then it can kind of start from one end of the candy graph, run the quantum algorithm for the glue trees problem, go to the other side, read sort of whether there's an even number of loops or not, to decide whether the original vertex was a leaf or a body vertex. On the other hand, kind of we know that a classical algorithm cannot sort of read this advice so easily, this advice about whether, or marking about whether a vertex is a leaf or not. And therefore, kind of a classical algorithm gets just totally lost in terms of deciding whether a graph is of this form or far from it. Okay, so guess I don't have too much time. I'll just say really quickly what the open questions are. So thank you so much for your attention and the opportunity to speak here. So the first open question is that we kind of showed R of F is Q of F to the 3P for computing P-uniform hypergraph properties in the adjacency matrix model. But the question is essentially, is this tight? We don't actually even know if this is tight for P is equal to 1. The second thing is, so we have a characterization theorem. It is only near complete. It'd be great to make it complete. The third is, and this is sort of, if we go back to this graph is too convoluted essentially to be of any relevance in the real world, and it would be great if we could come up with a graph property testing problem in the adjacency list model that is actually relevant for things we want to do in the real world. So yeah, we'll end with that now. Thank you very much.
Questions in the audience? Or any online?
Someone in the chat?
Nothing online right now. If anyone has a question at the Zoom, you can raise your hand.
In the meantime, maybe could I ask a question? Oh, yeah, so my question is about your summary slide where you have this beautiful decision tree.
Yeah.
So there, at the second junction, you have a large base size, primitive versus imprimitive. If you are primitive, then you say has an adjacency matrix hypergraph symmetry, and that's not a good thing. And then at the very end of, the right bottom corner of your decision tree, there you were in primitive, and then you brought it into the primitive parts, and now none has a small base size, and you said that was the open case. So why, in that case, you cannot apply the previous argument? Seems to me that once you have broken the imprimitive action into a primitive pieces, now why can't you apply to each piece the argument that you applied before when you said has an adjacency matrix hypergraph symmetry? Why does this? You're dealing now with large primitive blocks. Why does the same argument not apply?
I see. I think, yeah, if memory serves, I think it's somehow like it's less to do with, so each component is fine, but the way that they're combined together is by like these Rees products. And I think like the way that the thing kind of these primitive blocks gets combined together is the thing that could, our techniques cannot, show that those kind of structures also only admit small quantum speedups.
Okay, it has to do with the composition of these.
Yes.
Okay, good. Thank you very much. Michael,
Looks like no more questions. So,
So should we thank the speaker again?
sure.
yeah, thank you, Daochen.
Thank you so much, Robert.